see from the title of my talk, I'll be talking about some kind of operational approach to define a resource theory of purity, which is important for the foundation of thermodynamics. So this, as I said, is part of a larger project aimed at finding some kind of information theoretic foundation of thermodynamics, specifically in using the framework of generalized probabilistic theories. So first of all, let me recall what resource theory is. So in a resource theory, as the name says, we have something very important, maybe for some kind of task, which the so-called resources, and then we study the transformation between resources. So some of the resources are very abundant, so we call them free, whereas others are costly and because they are available for some specific tasks. And for the same reason, we have that a subset of all possible operations transforming one resource into another is very easy to implement, and so we call it the set of free operations. Although these operations are free, they consume the value of resources, so they give rise to a pre-order on resources. So whenever we have a free operation going from a resource A to a resource B, we say that A is more valuable than B, because this kind of free operation eats some value of A and gives some kind of less valuable resource. So here I'm particularly focusing on one of these resource theory, which is the resource theory of purity, and the quantum mechanical version was introduced in this form by Horodetzky and Oppenheim. So according to this resource theory, we have that we have a single free state, which is the maximally mixed state, because here we think of pure states as being the resource, the valuable resource of our theory. And the operations are so-called noisy operations, and they are built based on this structure here. So we have this kind of basic noisy operation, which are of this form. So we have a state, then we append some maximally mixed state, then we let them evolve, and we trace out the ancillary system. Unfortunately, or maybe fortunately, depends on the point of view, this set is not closed from the topological point of view. This means that since we want that every, let's say, operation that can be arbitrarily well approximated is a physical operation, then we also require that the set of all this transformation is closed. So we take the topological closure of this set. So the fact that this wasn't closed was pointed out by Shor. So why is this important for thermodynamics? Well, first of all, because we know that the maximum mixed state is the thermal state of a trivial Hamiltonian, and then we can regard free operation as something that has something to do with thermodynamics, because we have preparing thermal states, then putting a system into contact with a thermal environment and let them evolve, and then we remove the thermal environment. So this represents a toy model for thermal interaction. So the question is, does this work only in quantum mechanics, or is it something deeper in this framework to characterize this kind of thermalization processes? So in order to understand this question, we are going to move from the formula of quantum mechanics to generalized probabilistic theories, specifically using operational probabilistic theory, which were extensively introduced yesterday by both Alex and Opnian. So that's basically the outline. So first, we study different ways of defining purity in general probabilistic theories. So we have a first definition, which is more operational and relies on fewer assumptions, and then we see what other definitions of purity can be put forward in theories if we add some further axioms. So let's start with operational purity. So, as I mentioned, we are using this kind of framework, operational probabilistic theories, which are just a combination of the general probabilistic framework and the categorical framework. So we are using this kind of graphical notation and diagrams to prove theorems. So we have states, effects, as you heard in the tutorials. And I want in particular to point out this definition of reversible transformation. So we have that the transformation U is reversible whenever we find another transformation that does it, and such that we have, when we compose it on the left and on the right with this kind of inverse transformation, we get the identities of the standard notion of invertibility. Okay. Okay, so when we start analyzing the problem of purity in general probability theory, the first thing the first problem we face is that in general the maximally mixed state, here we call it invariant state because we don't have some kind of predefined notion of mixedness or of ordering of states according to their mixedness. So invariant state in the sense that it's left invariant by all reversible transformations. So in general this may not exist. Second point, if it exists, it may not be unique. Whereas in the framework I presented before, we're assuming that there were only one free state, which was the maximally mixed state, the invariant state. And even though, even if these two conditions are fulfilled, when there's maximally mixed state and it's unique, there may be another problem, because in the framework outlined, general framework of resource theory outlined by Kuke, Fritz, and Speckens, there's the requirement that free state should be stable under tensor product. But in general, the tensor product of parallel composition of invariant states is not invariant. So that's another problem we have to face. So the gist of this analysis is that in general we can't follow any of the approaches relying on the existence of an invariant state in general probabilistic theories, but we have to take another approach. So in this vein, I mean, we find that the best approach to define purity is via random reversible channels, here abbreviated as rare, and this was introduced for the first time in quantum mechanics by Ullmann in 1971. And so what we have here, so our free operations are just these channels of this form, just a random mixture of reversible transformations. So these represent some kind of ignorance about a reversible evolution on a closed system. So, and here we define the preorder. So we say that rho is purer than another state if we manage to find a rare channel connecting rho to the other state sigma. And note that there is no reference to the invariant state at all. So this is a good candidate for definition of the resource theory of purity in general probabilistic theory. So these properties, the properties of this kind of preorder and relation, and its relationship with the entanglement resource theory was studied in this paper, where we managed to prove a duality between the purity of marginals and the entanglement of the purification. So essentially, the more a state is entangled, the more the marginal is mixed. So that's how it works. So now, I mean, the main subject of this talk is whether it's possible to put forward other definition of purity, because it's very general. Now we want to get closer to quantum theory and use some kind of definition that make use of the invariant state somehow. So can we do that? Of course, in general this is not possible, as I said, for the reasons I outlined before. So what we have here is that, first of all, we must guarantee that an invariant state exists. In general, this is not true. It's unique. We want to get closer to the framework of quantum theory and the situation there. And moreover, we need to require that it's stable under tensor product, because in this way we are guaranteed that the set of free operation form a subcategory of the category of all the processes allowed by the theory itself. Of course, this is not possible to be done in general, so we need to introduce some further axioms. So what axioms to choose in order to achieve this? Well, maybe we don't want the most general ones, but we want some axioms that sound reasonable from the thermodynamic point of view. That's it, because remember that our ultimate goal is to recover the information theoretic structure leading to quantum thermodynamics. So our axiom should be of this kind of important for thermodynamics and some relevant for them. So let's start with a list of axioms. So the first one is purity preservation. So purity preservation states that whenever we compose either in sequence, which means one after another, or in parallel, which means perform on different systems, two transformations that are pure. Pure means that can't be refined or decomposed further as more elementary transformations. What we get is another pure transformation. As particular instance of this, we had that the product of two pure states is pure. Usually this is proved by relying on local tomography, but here we prefer going through this way, I mean, by using this kind of more fundamental axiom. And why do I say that this is fundamental? Well, because if purity preservation were to fail, so if we would lose information simply by connecting devices without having any specific physical process accounting for that. So just everything, information is lost simply in the wire when we connect devices. So there's nothing physical going on, simply just because we are composing things. And this would constitute also a serious limitation for experimental realization of the theory, because if any time we connect two things, we lose information, then building any kind of experimental apparatus would be a failure, because after a while we would lose the information completely. That's why we want to assume this. The second axiom is causality, as Ognian thoroughly said yesterday and examined with great detail. So essentially this means no signaling from the future. So why should I care about that? Well, actually I care more of this equivalent definition or equivalent statement that causality is equivalent to having a unique deterministic effect for every system. And this is important because when I have a unique deterministic effect, I have a canonical way of discarding information. When I have a bipartite state, for example, or a larger system, I can always restrict myself to a subsystem by forgetting or discarding some information by means of this deterministic effect. That's why I care about that. And indeed, in thermodynamics, one of the basic thermodynamic operation we do is just when we have a large system, we want to describe the behavior of a subsystem. So we need to be able to have a way of discarding information. That's it. But maybe we need also the opposite. I mean, going from one subsystem, we want to be able to reconstruct the picture of a larger system. And to do that, we need the following axiom. So this is purification. So purification states that whenever we have a state, even with partial information, like a mixed state, we can see it as the margin of a larger system in a pure state. So essentially, partial information arises because we are forgetting something. So in principle, we can always retrieve it. It's not a physical operation, but in principle, the theory admits such a level. And the second part of purification is the so-called essential uniqueness. So when we have two states that give rise to the same, that are the purification of the same state, so they give rise to the same marginal when we trace out, it means that they differ only by a reversible transformation on the purifying system. So somehow the dynamics of the system or the choice of the purification is blocked or almost blocked by knowing system A. So once we know A and the state of A, rho, then the choice of purification is almost fixed by, because the only freedom we have is just to apply a reversible transformation on the purifying system. And this reversible transformation arising in the purifying system is the source of all reversibility arising from purification. So, as I said, purification provides a simple way, a nice way of connecting irreversibility and partial information with a level where everything is pure and reversible. And all dilation and extension theorems in quantum theory were reconstructed axiomatically from this purification postulate. And it means that also, say, rephrasing it in more thermodynamic terms, whenever we want to enlarge maybe an open system to deal with an isolated system, we are formally justified in this procedure. So in classical mechanics, it's just a heuristic procedure. It's not built in the formalism. Instead, with purification postulate, we are guaranteed that we can do that even from the formalism itself. Clearly, I believe for this reason that purification is a good starting point for, say, a consistent or reasonable theory of thermodynamics, but unfortunately is not satisfied by classical theory. So this more or less tends to suggest that that theory of thermodynamics is ultimately quantum or something like that. Well, going instead, restricting to a more limited, say, aims. So purification guarantees that for every system the invariant state exists and it's unique. So that's a good starting point as well. Then let's move on with other axioms. Then we have the so-called pure sharpness axiom. So here for every system we have at least one pure effect occurring with probability 1 on some state. So what does it mean? So we can think of this pure effect as testing some kind of elementary property of the system. Elementary because it's pure, it can be further decomposed. And by assuming pure sharpness, we say that every system has at least one elementary property, in a sense. Then the last axiom, or axioms, then we'll see what happens. So suppose we have two sets of perfectly distinguishable, maximal sets of perfectly distinguishable pure states. We may think that these states encode classical information in any system, like in quantum mechanics we have that orthonormal basis can be used to encode classical information. If we assume strong symmetry, which means that whenever we have two such systems, such sets, we are able to find a reversible transformation connecting them, this is equivalent to saying that all the ways of encoding classical information in such a theory are equivalent, so there isn't any preferred set of that, so it's some kind of democracy or reversible, or of a set of perfectly distinguishable pure states. This is the strong version called strong symmetry, appeared in this work by Carlo, Müller and Ududek. There's also a weaker version called permutability. So in the permutability version we require that only permutations are implemented in a reversible way on maximal sets of pure states. So clearly, strong symmetry implies permutability. In general, the converse isn't true, but the interesting thing is that under the previous axioms, which means purity preservation, causality, purification, and pure sharpness, permutability is enough to guarantee the validity also of strong symmetry. That's the interesting thing. Then you may want to ask, so what theories satisfy these axioms? Well, unfortunately we don't have many examples. So concrete examples are real, complex, fermionic quantum theory, but also we have higher order interference variants of them, which are not explicitly formulated or stated. So we don't know essentially what further concrete example are there, I mean, beyond real, complex, and fermionic quantum theory, but in principle they are, because we know from the paper by Müller and Ududek that the axiom I mentioned, which guarantees spectrality plus strong symmetry, are not enough to guarantee, to derive quantum theory. We need to impose some other axiom, like the absence of higher order interference. So there are other things other than quantum theory in this picture. Okay, so let's see some consequences relevant to our work and our presentation. First of all, so in principle, I mean, all the states, the sets of perfectly distinguishable pure states that are maximal may have different cardinality in the theory. But under this axiom, we can prove that for every system, non-trivial system, there is an integer which is greater than or equal to 2, characterizing the size, the number of elements of such sets. So all of them have the same cardinality. Then we can prove what Hardy called the information locality axiom. So here, instead of being an axiom, it's a consequence of our axiom. So if we call this integer characterizing the size of maximal sets of perfectly distinguishable pure states, so we have that the size of the dimension of a composite system is the product of the dimension of the components. So that's the result in so-called information locality. As a consequence of this, we managed to prove that invariant states are stable under tensor product. So whenever we have an invariant state and another, we compose them, we get another invariant state. So now that's a good point, because now we can start to consider other ways of defining the resource theory of purity, not based on random reversible transformation, but based on the existence of the invariant state, which will be considered as the free state of our theory, like in quantum theory. And then, so the interesting thing is that to achieve these results, so we strongly think that actually permutability, strong symmetry, because they are equivalent, are not necessary actually. So we can derive them only based on the other axiom, which means causality, purification, purity preservation, and pure sharpness. So the last thing, which may be too strong according to some point of views, but it's not actually necessary. So what we have here is that now we can start defining a resource theory of purity based on the invariant state. So we declare that the invariant state chi is free, so we know that it's unique, it's stable, so it's well defined. So the most general class of transformation leaving chi is invariant is would be the most general definition of free operation in any context preserving the purity, preserving this kind of purity. And so we give this definition of unital channels even in general probabilistic theories satisfying these axioms. So we say that the channel is unital or doubly stochastic if it preserves the invariant state. That's it. So as it's very easy to see, rare channels are a particular instance of unital channels, but the converse isn't true, because we have this counterexample in quantum theory by Landau and Streeter in 1993, where they managed to show an example of a unital channel which can't be written as a convex combination of unitary channels, in our case, which means reversible transformation. So since quantum theories satisfy our axioms, then we conclude that even in this more general picture, including other theories than quantum theory, we have this strict inclusion of random reversible channels inside unital channels. Then we want to define also noisy operation and study the interplay between rare channels, unital channels, and noisy operations, and how they are related to each other. So again, as in quantum theory, we define the channel n from a system A to another system A to be a noisy operation if it's of this form. Again, we have the system, we have an environment E, we feed this invariant state to the environment, representing some kind of thermal bath put into contact with our system. Then we allow some kind of reversible interaction, because we consider the whole thing as an isolated system, and then we discard the environment, we get rid of the environment. Again, this is a good candidate to describe the thermalization process. Again, in quantum theory, this set isn't closed. Since quantum theory satisfies our axioms, then in general also this set isn't closed, so we have to take the topological closure. Again, because when we are able to approximate something arbitrarily well, we want to be able to say that that operation is physical, so it's free. So what happens here is that noisy operations are unital. So this is true as long as we have that the product of invariant state is invariant. And this is very easy to see, because if we plug the invariant state here, then we have that the product of this chi here plus the invariant state here is also an invariant state. And being invariant, this is left invariant by the reversible transformation. And then when we discard half of it, we get another invariant state. That's a very easy proof. But of course, we need to know that when we compose pure maximum state or invariant states, we get another invariant state. Again, in quantum theory, there's a counterexample. So not all unital channels are noisy operations. So again, we have this kind of strict inclusion. What about the rest? So how to rare channel interplay with these other notions? Well, under the axiom I presented, we can use a tool which will be presented in the next talk by Lee and Selby, which is the tool of controlled reversible transformation. We can prove that rare channel actually can be described as a particular kind of noisy operations. Again, here not all noisy operations are rare. There's a counterexample by Shor. So just to conclude, we have established this kind of strict inclusion between the class of channels. So we have that the most restricted class of channels are rare channels, which require fewer axioms. Then we have noisy operations, which strictly contain rare channels, and then we have unital channel, which strictly contain both of them. The interesting thing is that, so we recover the same behavior as in quantum theory without being in quantum theory and allowing for more general theories. And unfortunately, I don't have time to talk about this. That as it happens in quantum theory, what we have is that despite these strict inclusions, the preorder induced by these different classes, different sets of free operations, is the same under our axioms. It's just described by majorisation. And so with that, I would like to thank you for your attention and leave you with some references.
Questions? Comments?
Any question that pertains to what everybody's slide we were talking about I forget what you call the axiom.
The same slide. Can you say it?
You compose
The purity preservation axiom.
pure states in particular. You should always get pure states. Mentioned that
This one, I guess, right?
one part of that is when you take a composite or tensor product of pure states, you should get a pure state.
Yes.
Now that I think that should rule out criterion.
Exactly. Exactly, it does.
Then now the question is this: you said, look, if that were to fail, then when we combine systems of pure states, we would lose information. I don't quite see how that follows. If I combine two criterionic systems of pure states, the total state admittedly is no longer pure,
Yeah.
but the state space I've constructed has a much greater dimensionality. So what's it about information distinction?
Well, because if we think of, let's say, pure state as having the maximal information, then everything which isn't pure, then we say that we have lost some kind of information in this picture.
But he says that it's mixed in a bigger state.
Yeah.
So you simply mean in a sort of entropic sense.
Yeah, that's what I meant in my presentation. Yeah, I agree. In the sense that the space is larger, but I understand that maybe, yeah. So we are not actually able to describe the whole space completely because it's much larger than the others. Yes, but I was sticking to more to the operational level, such that in that case, mixed means just not having perfect control of information.
But formally then, if you calculate the mutual information of that product with something else, it wouldn't be smaller because it's fully preserved in the bigger state. Some entropy wouldn't increase.
Yes, definitely. Although here, this kind of notion is, I'd like to. So the issue of entropies in general probabilistic theory is a little bit tricky. So we have to be very careful when we define that, because in general we have to. So entropies are not able to fully capture what's going on in terms of purity intended in this kind of operational terms, and purity described by means of measure of mixedness by means of neutral information and relative entropies and other things like that. So the two things coincide only if the theory is well structured. So I wouldn't take this as some kind of measure of purity in a theory.
So you do have examples when they don't coincide, because this last thing which you said that it's all always majorisation would suggest that,
yes.
they will coincide.
Yes. Well, let's say we don't have concrete examples. So in general, in general probabilistic theories, we can define two different entropies, so-called measurement entropies and also the decomposition entropies. One is based on probability extracted from measurements, and one is based on how to decompose a state and on the probabilities arising in convex mixtures. So the thing is that some of the results are still ongoing is that with these axioms, these two entropies coincide, and in this case, they have this kind of nice property to capture the concept of majorisation and purity according to this kind of result theory, according to the, let's say, algebraic and operational structure of the theory, and so they all coincide in that case, but we need this kind of very special structure.
One more quick one, if anyone has. Yep.
If no one else has, where I might have missed a slide that assumes that, but at some point you say that you get an integer that gives you the dimension of a space. Which axiom rules out infinite dimensional systems?
Oh, well, actually, I should have said this from the very beginning. So we are restricting our attention in this analysis only to finite dimensional systems. Otherwise, I mean, clearly the invariant state doesn't exist in these operational terms.
So you say something like there exists one such maximal set of probabilistic states.
The proof to derive the results assume at some point that the process is involved in deriving the results have some kind of finite number of terms.
Sure.
Let's thank the speaker again.